Good morning everyone, thank you for joining me for this video. I am Mr. Ish and I'm presenting here a derivation video on the volume of cones. We know the volume is 1 over 3 pi r squared h. Very recently I pushed out a video where I showed how the volume of a sphere can be derived. All of this using integral calculus. Here we're looking at a cone. We already have the volume ahead of us, before us, and all we have to do is see how integral calculus can derive or help us derive this volume, and it's actually a very interesting procedure. You could look at volumes in a vertical manner. You could have something which looks like this in terms of a shape. You know, within this you have a right triangle that can form, or you can look at cones which have a horizontal aspect to them. In each instance you have some sort of a length dimension and a radius dimension. You can call this r, and my height can be the length dimension. We can say this is h and this is r, and in each instance you can make these slices. You can cut out slices, and when you push out the slices you're essentially looking at cross-sectional slices of what happens to be a circle. And then you have a radius, of course, and then you have a pi r squared. Again, if you pluck out these type of slices, vertical slices, you'll have vertical, but they're still slices of circles from a cross-sectional point of view, and each of these has a pi r squared. And as you now have become familiar with, when we're talking about volumes, we're looking at some sort of integration or limit of sums involving areas, because you're looking at the cumulative effect of the area calculation of all these slices that form of circles, or for whichever shape that might form based upon the initial volume shape you're looking at, and then you take the cumulative sum of those areas. You can always look at things along a dx perspective. This would be something like that, a dx perspective, sum a to b, or you can look at things along a vertical perspective, line of axis which is vertically oriented. You can say c to d, here would be a y dy. In this video we will look at this volume determination using both perspectives, so we're comfortable with both of them. The first way that we look at this volume of a cone derivation is using that template with regards to dy. You know, when you're looking at equations with respect to dy, you have to present vertically oriented intervals, and your equation must be x equals format. If you draw a line from right here to right here, and you call this r comma 0 and you call this 0 comma h, you can very well start this determination process. How will you do it? You will take this little curve and you rotate it around the y-axis. Y-axis rotation. When you do that, you get your cone, a vertically oriented cone, which is what you want, because that's what we're looking at things first. If you take any of these slices out and you pluck them out, you actually have a circle which forms, which has a horizontally oriented radius, and you know it's coming off this vertically oriented height, hence 0 comma h and r comma 0. Each of these circular slices can easily go through a area formation, derivation pi r squared, which then gets integrated. What we have to do is determine this first, and that's usually the hardest part of these type of questions. So the first thing we have to do is determine the radius, and the way we can do that is by determining the equation of this line. And from any point from your line of axis, which is y-axis, to any point over here will always represent a certain distance, which will be your radius, because it's always determined from your line of axis or your line of rotation or your line of dynamic movement. We have 0 comma h and we have r comma 0. A linear line will develop y equals mx plus b. The slope here will be minus h over r, and the equation will be minus h over rx plus your y-intercept 0 comma h. But since we're looking at integration here with respect to dy, we have to convert this into x equals format. It will be x is equal to y minus h times minus r over h. You can open this up. You'll have minus ry over h plus r. The h's cancel out. This right here represents the distance from your line of rotation to your line, which also represents your radius, and this now must go through pi r square formula so that you can go through that integration process. When you do this pi r square of this part, it's not hard. You're just doing a polynomial and multiplying by the same polynomial. You're getting positive r square y square over h square plus r square. Remember, a minus b times a minus b is equal to a square minus 2ab plus b square. Here's my a square and my b square component. Now I have to do my minus 2ab. So you get a 2r square y over h. And you can always do this on the side and you can verify that this is right and it should be right. This right here represents my ay, which will be integrated, and here it is. Now we have to determine our intervals. Our intervals are right here from this origin point to this height 0 comma h. From 0 to h, y-axis intervals, lower limit, upper limit, and you have all of this which has to be integrated, r square y square over h square plus r square minus 2r square y over h. With respect to dy, this entire derivation procedure with respect to dx is easier. So again, we started with a figure, we determined the line of our curve, we understood how to determine the radius, and the radius went through the pi r squared, the area formula, because each of these resulting slices is a circle, and the circle area is what integrates from your lower limit up to your upper limit. And we have to do this. This is a very easy integral because it's a polynomial. Everything with respect to y, with the y's coming in. You'll have a r square, you have a y cube over 3h square. Remember y, 2 plus 1 divided by 2 plus 1. Here you'll have a r square y. Here you have a 2r square y square over 2h. From h to 0, bring in the h's in places of y's. Zeros are meaningless. You'll have r square h cube over 3h square plus r square h minus 2r square h square over 2h. You can cancel out some h's and these 2's. When you cancel them out, here this h squared cancels out, you get r squared h over 3. Here you have an r squared h. Here the 2's cancel out and one h cancels out. You have a r squared h. This cancels out with this. You're left with this pi sitting outside. You have a pi, you have an r squared, you have an h over 3, and here's your volume with respect to y of the cone, which would have developed from this rotation movement or dynamic movement around the y-axis, and it would look something like that. And the formula has been derived. Now we end this video with the determination of this volume of the cone. The same formula will be determined, but we look at things along the dx. You know, when you're looking along dx, integrating with respect to dx, you present equations y equals format, and you have horizontally oriented intervals, lower limit and upper limit along a horizontal axis. It doesn't have to be x-axis, it could have any horizontal line. But look here, we have 0 comma r and h comma 0, so the coordinates are flipped. The reason why I flipped the coordinates, because if you were to draw a horizontally oriented cone and you were to take this slice out of this circle, in this direction you have this line going across, but you have a radius which is vertically oriented, and your height of the cone or the length of the cone is horizontally oriented. Hence the points are the way they are. If you do here now rotation along the x-axis, so we're doing rotation here along x-axis, and that's how this dynamic movement is created. We have points 0 comma r and h comma 0, from which you have to determine the equation of a linear line, which will then go through this radius and rotation effect. We have 0 comma r and we have h comma 0. M here, the slope is equal to minus r over h. Y, the equation nx plus b is equal to minus r over hx plus r, my y-intercept. This right here represents any distance of any point from this line of axis or rotation up to any point on this curve. This, specifically this is here your radius, and you know these slices which are generated right over here represent circular slices. When you look at these circular slices, you have an area which is pi r square, which has to be integrated there, but you already have your radius, which is this. You have to send it through this pi r square formula, and this is what you get. You have a minus r over hx plus r whole square pi r square, and this is no different than doing a minus b times a minus b. You'll get pi. Here you get r square x square over h square plus r square minus 2 r square x over h. The only reason why you're getting an r square here is because when you do a minus b times a minus b, this r will multiply with the r over here in the counterpart parentheses, and you get the r square. So here's my pi r square, which has to be integrated here. Now we have to look at our intervals. Intervals is from here 0 comma 0 up to this h comma 0. So from a 0 to h, these are your x-axis dimension lower and upper limits. Here's my formula. I'm just pushing the pi out as a coefficient. I have r square x square over h square plus r square minus 2r square x over h, and dx. Let's do this. Integrate it. It's easy. Everything with respect to x. R square x cube over 3h square plus r square x minus 2r square x square over 2h. We're just bringing in the x's, the new x's, by the x into n plus 1 or n plus 1 polynomial integration template technique. That's how these values are coming about. Now we have to just upper limit h, lower limit 0. Upper limit is meaningful, 0 is meaningless here. You'll have r square h cube over 3h square plus r square h minus 2r square h square over 2h. You can do some cancellation out. You'll have pi over here. You'll have an r square h over 3 plus r squared h minus r squared h. This cancels out and you get volume here with respect to the x-axis dimension or a horizontal line of rotation. You'll have a r squared h over 3 and this pi coming back into the picture, or you can just say 1 over 3 pi r squared h, and it's done. So keep in mind these dynamic movements of curves give rise to volumes, and you can use integral calculus by taking area slices or slices of areas and integrating those along your interval, whether it's horizontally oriented interval or vertically oriented interval. And this is just but one technique. There are other techniques to do these determinations, such as the cylindrical shell technique. We are not there yet, but we will be in the near future, and I can show you some of these again using those different techniques. But this right here is volume of a cone determined using integral calculus and by applying the concept of dynamic movement, which is rotation of curves about a line of axis to give you a three-dimensional object, and by means of slices and integration of those slices you get the volumes determined. Thank you for watching. Have a nice day.